Assalamualaikum. My name is Nur Atirah Zahari from AS24560. My supervisor is Madam Nur Aisyah Abdullah. Welcome to my presentation to the panels. Today I'm going to present on my viva about the organocatalyzed asymmetric Friedel-Craft alkylation reaction and update. First of all, let me introduce about this study. Friedel-Craft alkylation FCA reactions refer to a method of generating alkyl benzenes by using alkyl halides as reactants. Scheme 1 shows an example of intramolecular FCA reaction utilizing organocatalysts. Organocatalysts are small organic compounds that have the ability to catalyze reactions in the absence of metal or metal ions. Organocatalysts are entirely organic, devoid of metals and made up of non-metals. These catalysts can be designed and synthesized relatively easily, and they are often stable. Furthermore, they use ferroprotective groups, so there are ferro reaction steps overall. Generally, sugars, peptides, and amino acids, alkaloids, and sugars are thought of as organocatalysts. Next, the first problem statement in this study is the recent development of organocatalyst asymmetric FC reaction has not yet been discussed from 2010 to 2020. Second, the study which covers all the significant and outstanding developments relevant to organocatalyst applicability in FCA reaction has not been emphasized. Next, we move to the research question. First, what are the developments pertaining to the use of organocatalysts in FCA reaction? Second, what are the substrate scopes of various catalytic reactions in FCA reaction? The objective of this study is to study the substrate scopes of organocatalysts in FCA reaction, to investigate the uses of organocatalysts in FCA reaction, and to critically review the literature about organocatalysts used in FCA reaction. Besides, the significance of this study is the recent development of organocatalysts in asymmetric FC reactions can be highlighted. Second, the review paper includes all of the major and noteworthy advancements relevant to organocatalysts and their application in Friedel-Craft reactions. Next, in this literature review, asymmetric FCA reaction have been used. 3 organocatalysts include chiral phosphoric acid, thioureas, and cinchona alkaloids. Table 1 shows the examples of the reaction that use chiral phosphoric acids as their organocatalysts. For the synthesis of alpha-trifluoromethyl tertiary alcohols, the organocatalyst used was Bronsted acid BH catalyst, shown in Figure 1, which efficiently catalyzed asymmetric FCA of benzotiazole and indoles, shown in Scheme 2. The reaction successfully gives up to 99% yields and enantiomeric excess EE. In general, Bronsted acid organocatalyst is useful to give excellent efficiency and enantio selectivity, mild reaction conditions, and low catalyst loading, simple operation and easy gram-scale preparation, and synthesis of enantio-enriched alpha-trifluoromethyl tertiary alcohols with 2 important heterocycles. For the synthesis of 1,4-disubstituted indoles, the organocatalyst used was arbinyl-derived catalyst shown in Figure 2, which efficiently catalyzed asymmetric FCA of E1,4-diphenyl 2-butene 1,4-dione and 4-benzyl aminoindole shown in Scheme 3. The result showed excellent regioselectivity and no byproduct was present. These catalysts successfully give up to 98% yields and 85% EE. Both electron-donating and electron-withdrawing groups were tolerated to give the corresponding products in moderate to high yields with good to high enantio selectivities. Table 2 shows the examples of the reaction that use thioureas. For the synthesis of plus trans dihydrolycoricidin, the organocatalyst used was guanidine or bistyuria catalyst, shown in Figure 3, efficiently catalyzed asymmetric 1,4-FC reaction of phenols and nitroolefins, shown in Scheme 4. The enantio selective construction of the cyclic ring resulting from 1,4-FC reaction successfully give up to 99% yields and 94% EE. For the FCA by thiourea functionalized MIL-101 CR organocatalyst shown in Figure 4, which efficiently catalyzed asymmetric FCA of indole and beta-nitrostyrene shown in Scheme 5, when the reaction was conducted in the presence of this catalyst in 30 mg by raising the temperature to 80 degrees C, the reaction successfully gave up to 84% yield within 18 hours, toluene was used as the reaction medium due to its significantly shorter reaction time. Table 3 shows the examples of the reaction that use cinchona alkaloids. For the synthesis of C3 symmetric cinchona, the organocatalyst used was the parent hydroquinone catalyst shown in Figure 5, which efficiently catalyzed FCA reaction of 1H-indole and ethyl 333-trifluoro-2-oxopropanoate shown in Scheme 6. The reaction successfully gave up to 82% yield and 73% EE. The synthesis of C3 symmetric cinchona is an efficient and simple access by FC reaction between 1H-indole and ethyl 333-trifluoro-2-oxopropanoate. For the synthesis of furo-2,3-benzofuranones derivative, the organocatalyst used was squamide catalyst shown in Figure 6, which efficiently catalyzed asymmetric FCA of 3-leadine-ox-indole and 2-naphthol shown in Scheme 7. The reaction successfully gave up to 83% yields and 90% EE. So, which one is the best catalyst? The best catalyst is chiral phosphoric acid, which is Bronsted acid BH catalyst. This is due to their acid-base activation. Chiral phosphoric acid possess both Bronsted acid and Lewis-base functionalities, allowing them to activate both nucleophile and electrophile simultaneously. This dual activation mode enhances the reactivity and selectivity of the catalytic process, making chiral phosphoric acids efficient catalysts for various transformations. Next, mild reaction conditions. Chiral phosphoric acid catalyzed reactions typically operate under mild reaction conditions such as ambient temperature and non-extreme pH values. This mildness makes the process more practical and compatible with a wide range of functional groups, thereby expanding the synthetic utility of this catalyst. Besides catalyst stability and compatibility, chiral phosphoric acids are generally stable and can be easily synthesized from commercially available starting materials. They are compatible with various solvents and can be readily recovered and reused, making them appealing from a practical standpoint. Next, chiral recognition. Chiral phosphoric acids can exhibit strong chiral recognition capabilities due to the presence of a chiral center at the phosphorus atom. This enables them to differentiate between enantiomers of substrates, leading to high levels of enantiomer selectivity in asymmetric reactions. The chiral environment created by the phosphoric acid moiety can effectively influence the stereochemistry of the reaction. In conclusion, the catalytic activity of various compounds commonly used in FCA by organocatalysts has been studied. The moderate catalytic properties of organocatalysts are able to reduce the production of side products. It also provided advantages in enhancing the product yield. Organocatalysts act as an effective catalyst for the FCA reaction with their own advantages that can be synthesized relatively easily, and they are often stable. Here are the list of future research recommendations for organocatalyzed asymmetric FCA reaction. First, catalyst design and development, which is exploration of new chiral organocatalysts for improved selectivity and reactivity. Second, substrate scope and reactivity, which is expansion of the substrate scope to include diverse aromatic compounds, heterocycles, and alkenes. Third, enantiomer selective variant development, which is development of enantiomer selective organocatalyzed asymmetric FCA reaction using chiral organocatalysts or auxiliary strategies. That's all from me. Thank you.